Hello students, welcome to EPG Pathshala. I am Reema Gupta from University of Delhi. So today students, we are going to discuss about the module that is Resonator, and it is from the paper Semiconductor Materials and Devices. So after studying this module, you all should be able to understand what is the waveguide, how the wave propagates, what are the different modes of propagation, types of waveguide resonators including strip line, microstrip line and coplanar waveguide, that is CPW mode. After that, we will be discussing on the applications of microwave resonators and tunable microwave filters. So, let's discuss about the microwave resonators. What are microwave resonators and why do we need them? So, microwave resonators have been widely used in various applications such as filters, oscillators, amplifiers and so on. Since the operation of the microwave resonator is very similar to that of lumped element circuit resonators of the circuit theory. So we will begin by reviewing the basic characters of series and parallel RLC resonator circuits. So for the communication through microwave resonator, the waveguide play a very crucial role. So in the initial stages of the microwave development, the rectangular waveguide became the dominant waveguide structure largely because of high quality component could be designed using it. So one of the main issue was its narrow bandwidth due to its cutoff frequency characteristics. In the present module, we will be discussing about the waveguides and then the type of waveguides. So, waveguides are very much necessary for the communication purpose, whether it is satellite communication or it is land communication, because the waveguides propose or they provides the minimum loss pathway to transfer the data from one place to another. In this module, we will discuss about the type of waveguides which exist. So, in the ancient time or in the earlier stage, for the higher frequency characteristics or for the higher frequency communication, the cables are used. But the normal coaxial cable provide lot of losses for the transmission in the microwave range. So to avoid such losses, the waveguides are come into picture. They provides the minimum loss pathway and guides the electromagnetic wave. So after the discussion of the types of waveguides, we will move to further topic, that is propagation of wave. We will be discussing about different configuration of the resonators, that is microstrip, strip line and coplanar waveguide resonators. So these different type of resonators are utilized such that one can integrate the resonator with the electronic industry or integrated circuits. The earlier waveguide structures are bulkier in size and it is difficult to integrate them with the another electronic circuitry. But with the advancement in the technology, it is necessary to reduce the size of the waveguide resonators such that they can be integrated with the modern technology. So let's discuss about different types of waveguide resonators one by one in detail. Waveguides. Waveguide is a metallic structure that guides the electromagnetic wave in a particular direction. They exist in form of wires, coaxial cables or parallel plates. The optical fibers are also used as waveguide for electromagnetic waves. In general, the transmission of electromagnetic radiations, though in free space, is subjected to diffraction, which results in spreading of energy. This problem has been resolved by the waveguides at the expense of material structure. The waveguide enables a signal to propagate with minimal losses of energy by restricting expansions to one or more dimensions. A waveguide is a special form of transmission line consisting of a hollow metallic structure, which you all can see in this figure. The walls of the waveguide represent the distributed inductance, while the empty space between the walls provide distributed capacitance. Waveguides are utilized practically only for the signals of extremely high frequency, where the wavelength of operation approaches the cross-sectional dimensions of the waveguide, and for lower frequencies, waveguides are of no use. Now comes mode of wave propagation. The electromagnetic wave consists of electric and magnetic field perpendicular to each other but propagate in the direction of propagation. The electromagnetic wave propagates through the waveguide in three ways, which are: first is transverse electric mode, that is TE mode. The second one is transverse magnetic mode, that is TM mode. And the third one is the transverse electric and magnetic mode, that is TEM mode. So when an electromagnetic wave propagates down a hollow tube, only one of the fields, that is either magnetic or electric, will be transversed to the direction of wave propagation. However, the other field will loop longitudinally to the direction of wave propagation. But the two fields, that is electric and magnetic fields, will remain perpendicular to each other. So, when the electric field is transverse, then it is called transverse electric mode, and when the magnetic field is transverse to the wave propagation, it is called transverse magnetic, that is TM mode. However, in TEM mode, both electric field and magnetic fields are perpendicular to the direction of traveling wave along the length of a normal transmission line, which you all can see in the figure on the right hand side. The TEM mode exists only where there are two conductors present, and it is dominant mode where the cross-sectional dimensions of the transmission line are small as compared to the wavelength of the signal. TEM mode is also known as the differential mode because the signal flowing on the inner conductor is directed opposite to the ground signal flowing on the outer conductor. So in TEM mode, at least two unconnected conductors and a single insulating material are required for it to exist, and its cutoff frequency is 0 Hz. So there exists one more mode, that is quasi-TEM mode. So here, quasi-TEM mode, we have discussed, it is quasi-transverse electric mode, which is utilized in the transmission of waves. As discussed earlier, the TEM mode is transverse electric and magnetic mode, which exist in the structures having two conductors surrounded by the dielectric medium. So the quasi-TEM mode is very much similar to the already discussed TEM mode, but it is present in microstrip resonators and coplanar waveguide resonators. So due to the presence of two different medium having different resistivities, the wave propagation occurs where the wave propagate with different speeds in both the direction. So this results in quasi-TEM mode. So quasi-TEM mode is also known as hybrid mode, which has non-zero electric and magnetic field in the direction to the propagation. So the hybrid modes are higher modes which occur with cutoff frequencies different from the direct current, that is 0 Hz, and are undesirable. Types of waveguides. As we have discussed, the waveguides can be developed in three ways. The first is strip line, the second is microstrip line, and the third one is the coplanar waveguide. So let us discuss all of these one by one. So here comes strip line waveguides. Strip line is the type of waveguide which requires 3 layers of conductors, where the internal conductor is commonly called the hot conductor or stub, while the other two are always connected at the signal ground, which is known as cold conductor or simply ground. The stub is embedded in a homogeneous and isotropic dielectric of dielectric constant epsilon r. So unlike the case of microstrip, the substrate is not appropriate since the dielectric completely surrounds the signal conductor. So students, you can see in this figure for the strip line, so left hand side show the section of a strip line, whereas right hand side shows the propagation of electric and magnetic fields. Because the region between the outer plate of a strip line contains only a single medium, the phase velocity and the characteristic impedance of the dominant TEM mode do not vary with the frequency. So in the fundamental mode, the signal conductor is equipotential, that is, every point in it is at the same potential. The strip line is often required for multi-layer circuits boards because it can be placed between the layers, but the grounding between the strip line requires more care. So in this case, the top and the bottom ground planes are not at the same potential. Therefore, the parallel plate mode can propagate between them. So if excited, this mode will not remain confined to the region near the strips, but will be able to propagate wherever the two ground planes exist. So the strip line is more sensitive than microstrip line to the lateral ground planes of a metallic enclosure, since the electromagnetic field is strongly contained near the center conductor and the top-bottom conductor ground planes. Now the second category is the microstrip waveguides. The microstrip technology consists of a thin conducting strip placed on a dielectric substrate. The bottom side of a substrate is covered entirely by metal and serves as the ground plane. The substrate is characterized by its dielectric permittivity and thickness. So it serves as a mechanical support and as a medium for electromagnetic field propagation. So in 1975, the Hammerstedt proposed the first equation to compute the characteristic impedance of a microstrip line. It is proportional to the ratio of the strip width over the substrate thickness. Since then, the additional equations have been proposed to account for the strong dispersion of microstrip lines at millimeter wavelengths. In simple terms, microstrip is the printed circuit version of a wire over a ground plane, and therefore it tends to radiate as the spacing between the ground plane and the strip which increases. The microstrip line is a dispersive in nature, and with increasing frequency, the effective dielectric constant gradually increases towards that of the substrate, so that the phase velocity decreases. However, it is also valid for non-dispersive medium. The third category is the coplanar waveguides. So among the three categories, the coplanar waveguide, that is CPW, is the most successful geometry for the transmission of electromagnetic wave in the microwave region. In general, the coplanar waveguide consists of a central conductor and two ground planes printed on the same surface of the dielectric slab, which is shown in the figure. The coplanar line has basically two dominant modes of propagation. One is quasi-TEM mode, that is transverse EM mode, which is also known as odd mode or coplanar mode, where the field in the two slots are 180-degree out of phase, as shown in this figure. The other is non-TEM mode, called the even mode or the coupled slot line mode, where the fields are in phase as shown in the figure. In CPW microwave circuits, the coplanar mode is the most desired due to its low radiation property. The excitation of unwanted slot line modes can be avoided by either maintaining the symmetry of the CPW structure or using air bridges, so that to connect the ground plane of the CPWs. So what are the applications for the microwave resonators? So here come its answer. The satellite communication plays an imperative role in the navigation of moving aircrafts, detection of water pollution, oil field monitoring, weather conditions, war fighters, virtual connectivity on Earth, and so on. And they work at RF and microwave frequencies. The first initiative towards the fabrication of microwave filters was carried out during Second World War by a radio research laboratory where the broadband, low band, band pass, high pass coaxial filters and narrow band pass filters and resonators were developed by the radiation laboratory. The wireless communication systems are demanding tighter requirements in terms of electrical specifications as well as drastic reduction in manufacturing cost and development. So the area of microwave filters, especially for mobile and space applications, has experienced significant improvement with respect to the theoretical and technological aspects. So one of the significant improvement in filter design theory was utilized cross-coupling between the non-adjacent resonators. Early workers by Kutzuk described the third order and fourth order filters with cross-coupling. The multipath effect causes zero transmission to appear in the transfer function, which is dependent on the phasing of the signals, causing zero transmission lines at finite frequency or group delay flattening or even both. So along with the improvement in electrical performance of filters, many efforts have been made for the improvement in the miniaturization. Especially reducing the size and volume of filter has been the main topic for filter designs. The dielectric resonator filters have the advantages of not only small size but also temperature stability. Another major step in reducing the volume and mass of microwave filters was utilized having dual mode technique. However, Williams in 1970 also describes the fundamental theory of dual mode waveguide filters for the realization. The dual mode filters use two orthogonal degenerate modes of each resonator, where the number of resonators can be reduced by a factor of 2. Hence, obtaining small volume and mass become possible by using dual mode filters. Tunable microwave filters. Another microwave filters design technique having great potential in the tunable microwave filter design technique. For example, the frequency agile system for naval target control uses 19 channels from 421.5 MHz to 448.5 MHz. This frequency agile system can obtain improved resistance to interference and increase data link reliability. So it can sense interference and automatically changes the frequency to avoid any interface by switching from one filter to another. But the system should have many filters as the number of channels. Hence, compared to the bank of switched fixed frequency filters, tunable filters can make frequency agile systems more simpler. The resonators can be characterized into planar resonators and non-planar resonators. So they have applications according to their categories. Most common planar resonators are implemented using the microstrip structures. So the microstrip patch resonators and microstrip line resonators are the representative of planar resonators. Regarding reduction in the size of the resonator, the microstrip resonator line has great advantage over the cavity resonators, and most successful method to reduce the size of the resonator is meandering the microstrip line of the resonator. The meandered microstrip line open loop resonator is smaller than lambda by 8 by lambda by 4, where the lambda is the guided wavelength at the center frequency. So for further reduction of the resonator size, using meander line can be done, but however in general the quality factor of resonator becomes worse as the line becomes narrower. The disadvantage of the meanders line resonators has been overcome by high temperature superconducting materials which can be employed. So on the other hand, the non-planar resonators have relatively higher quality factor than the planar resonators. Although the non-planar resonators are bulky and each filter are employed by the wireless system where the electrical performance are much more important than the size and volume. So students, let us summarize what we have learned in this module. So students, first of all, we have discussed about what is waveguide. Waveguide is a metallic structure that guides the electromagnetic wave in a particular direction. They exist in form of wires, coaxial cables as well as the parallel plates. So the waveguides enable a signal to propagate with minimum loss of energy by restricting the expansion to one or more dimensions. Moreover, we have understood that the walls of the waveguide represent the distributed inductance while the empty space between the walls provide the distributed capacitance. The electromagnetic wave is consist of electric and magnetic field perpendicular to each other, but the propagation is perpendicular to the direction of electric and magnetic field. That is, the electric, magnetic and the wave propagation vector, all three are perpendicular. Then we have discussed that there are different modes of propagation, and we have discussed about transverse electric, that is TE mode, transverse magnetic, that is TM mode, and transverse electromagnetic, that is TEM mode. Then we have discussed about the waveguides for the different configurations. So the different possible configurations are the strip line, microstrip and coplanar waveguide resonators. So here coplanar waveguide resonators are represented by CPW resonators. And we have concluded that among the three resonators, the coplanar waveguide resonators is the most successful geometry for the transmission of electromagnetic wave in the microwave region from one point to another. So in general, the coplanar waveguide consists of a center conductor with two ground planes printed on the same surface of a dielectric slab. Thank you.